All right, so I'll be starting our presentation on what we did this summer. So what we did is we constructed a device called a Gaussian condenser that counts the number of air ions in the atmosphere at any given moment. So first, what is a Gaussian condenser? And it's a device just to measure the actual number of air ions present at any point in the atmosphere. And it's used mainly in meteorology to provide accurate measurements of ions. So it's in meteorologic predictions, atmospheric physics problems, and plasma physics. So the device at the heart of the Gaussian condenser is called a cylindrical capacitor. And we made ours with two thin copper sheets that were rolled into two different size tubes and placed into each other. And they're placed concentrically, so they're not touching each other. And the smaller tube is inside of the bigger tube. And there's a different voltage applied to each of the tubes, which creates a potential difference and an electric field between the tubes, because the tubes are exchanging electrons between each other. And then when charged particles go between the tubes, they hit this electric field and they experience a force. And them experiencing this force creates a current, which can be measured and analyzed to determine the number of air ions that are flowing between the tubes. Let's now discuss the Gaussian condenser's significance and applications to atmospheric physics as a whole. So there's two main ones. It's significant to meteorological predictions, and is significant to determining the health of the ozone layer at any point. So for the first one, a decrease of atmospheric ionization leads to a decrease of total cloudiness and a decrease of atmospheric turbulence, altogether with an increase in isobaric levels, which are surfaces of the atmosphere where the pressure is equal along a surface. And then as a result, since the decrease in ionization leads to a decrease of cloudiness and an increase in isobaric levels, you can expect a decrease in rainfall when you see a decrease in air ionization. So using the Gaussian condenser to determine the levels of air ions. And if you see a decrease in ionization, you can expect a decrease in rainfall at that point. And then the second main point of the Gaussian condenser in meteorology is determining the health of the ozone layer. So the ozone layer, O3 molecules individually ionize the surrounding atmosphere, which means that when the ozone layer is stronger, the surrounding atmosphere will be more ionized than when the ozone layer is weaker. And then if you use a Gaussian condenser to measure the ionization of the surrounding atmosphere, it's possible to determine the health of the layer by seeing if it's a high ionization or a low ionization. Okay.
Now you can introduce yourself.
Yeah.
Hello, I'm Iyan Syeed-Miller. I'm a senior at Pasadena High School. So design challenges. Before we started building this thing, there were four main complications that we knew about. Was that the current going between both the cylinders is going to be very small, way too small for our multimeters to measure. The electric field was the difference between the tubes was negligible in charge, so any current going between them was just air ions. And there's also radio frequency noise just in the background. Any radio frequencies could mess up our condenser, so we needed something to block that out. And as well, we have a circuit component to this thing, and that would be subject to the seeback effect, where every wire and circuit component we used would create a little bit of unwanted voltage in when there are different temperatures touching. So to mitigate that, to mitigate a small current, we utilize op amps to amplify our circuit, and with a high gain factor, we could get a measurable voltage out of our current. And for the weak electric field, we charged the outer tube to make an electric field that guided the ions into the middle ones so that they were detectable. In this case, we used 18 volts of bias on the outer tube. To protect against the radio frequency noise, we coated the entire box in tinfoil. So all of our circuitry and the condenser was inside tinfoil. The seeback effect, after we got our circuits working, we decided to condense them, making the wires shorter, removing any unnecessary components, and we grounded all of our components onto one ground just to make sure there was as least error as possible.
I'm Isaac. Zhang, and I am a rising junior at BHS, or Pasadena High School. For our circuit, there is three main components. The first component is the potentiometer. This allows us to calibrate the circuit so that the voltage going into the positive terminal of the first op amp is 0. And you can see the first op amp. There is the triangle with the negative and the positive sign. The first op amp is the transimpedance stage, which converts the current, which is about, I think, 100 picoamps, to voltage to about 100 microvolts. And then the second op amp is the voltage amplification stage, which amplifies that voltage by a factor of, I believe, 100, and using a negative feedback loop. Since both op amps are going, both voltages are going into the negative terminal for the op amp, the result causes the voltage to remain positive. So when we constructed our box, first we wrapped the box in foil to prevent the outside radio noise. And we also had 2 copper tubes placed in between the boxes. This allows us to generate the field. The fan is then added to the back of the tube. This creates a constant airflow, allowing for the readings to be more constant and fluctuate less. Then the breadboards are placed onto the box above the tinfoil box, and inside is wrapped with a covering of tinfoil. The switches are then added to the outside for convenience, and overall the circuit is grounded to the foil box. Okay. So the data. So for our data, we headed to the Eden Canyon waterfall to measure the air ions there. And essentially what we did was we grabbed our condenser and we measured the air ions in relation to the distance to the waterfall.
Along with the Eden Canyon data, we also took data here on the Caltech campus, just to get different amounts. So for our shade, sun, car, that's the exhaust from the back of a car, and the exhaust from a semi that was parked nearby and just idling. So these are the amount of picoamps that was measured, and the rest is an percent increase from the shade. There's also then here is about 129% increase from the waterfall. That was much bigger than anything else we measured here on campus. So here is everyone's data from the waterfall. All our condensers were calibrated a little bit differently. So you can see the same general trend, but just varying levels of it. Over here on the right is the equation we used to change our voltage into an actual amount of air ionization. So this is the coulombs. This is the voltage we measured, the offset from our calibration. This is the airflow. We couldn't get this on our own. We had to find other people who've done the condenser before and what they found at waterfalls. This is, oh, you can't see where I'm pointing. Can you?
No, you can't.
Oh, nice. This is just the charge of an electron, and here is the gain factor from our op amp circuit. So, hey, another snippet here is ions can be found at waterfalls because the water hitting each other discharges particles, and that's one of the few places you can get ions, along with places that have pollution. That's why the car exhaust is so full. All right.
And an explanation for why each data set is different, like actually different for measuring the amount of ions, is because each device is calibrated differently. So it measures a different amount of ions, but the general trend among it and the general percent increase should be similar. So for my personal data, what I measured was my experiment was rubbing a cotton shirt on a plastic bag near the input of the condenser. And I was expecting an increase. And so that the top data set was just when I measured it outside in shade. And what I got out of it was 10 millivolts. And then using a formula, I converted that into 2,389 air ions. So that was the number of air ions. And then in the experimental data, the minimum value I got over a time of around 20 seconds was 26 millivolts, and the maximum was 31 millivolts with an average of 29.3. So the number of ions was 3,817, which is, I calculated, like over 60% greater than when compared just to the shade. So, and then my hypothesis, I'm not actually 100% sure of this, but my hypothesis for why this value is so much bigger is because of an effect called the triboelectric effect, which occurs when two objects of different material rub or slide against one another and exchange electrons and ions. And then, so I believe that the condenser picked up on this exchange of ions, and some of these ions were pushed through the two concentric tubes in the heart of our condenser, which explains why it read a greater amount of ions.
So for my personal experiment, I tested two filters. This one I found at Caltech, which was in our room, and the other one is one from my house. The results vary, and I measured from a length beginning from 0 meters to 1.5, and the distance should be about the same for both of them. As you can see the trend from the graph here, I believe the filter from my house resulted in a higher air ion concentration at 0, but the Caltech had a lower air ion concentration. One of my hypotheses for this is just the Caltech one had a better filter and mine is slightly older.
So for my data, I measured how much the voltage would change. I guess that air ions would change if I left mine in the sun for a long time. So I measured it as in time in the heat. If the voltage increased over time, and with the average the table here is the voltage I measured, and I translated that to air ion concentrations over here on the graph. The average concentration overall was about 7,500 air ions, which is about 130% increase from the shade we measured here. To just keep it consistent, I had my measurement times was about 12:50 p.m. to 1:55 p.m. just in the middle of the day, and somehow the temperatures stayed relatively consistent for this. There's a little hole in my data where my multimeter overheated and I had to restart. But other than that, I think this shows good trend for sunlight. Oh, and here are the sources that helped us along the way. So they're just helped us learn how ions work and gradient condensers.
Thank you. I have the gradient condenser here. As you can tell, it's a little hard to get it over, but as you can see, there's the circuit inside, and the batteries are on top, as well as the switches and the fan for the airflow. As in the tube, it's a little hard to see, but it is in the inside of the box. All right, thank you.
Thanks.
Our mentor Robert's here and Dr. Bellan. Robert, do you want to comment?
Yeah, I think over the 6 weeks, they learned a lot about not only physics and theory, like with electric fields and capacitors, but of how to work with electronics, how to troubleshoot. And I think the waterfall is also a good combination of that, having good the ability to condense turn something down that has a lot of wires, and a lot of complicated circuits into something that you can bring into this room that won't break appliances. And also making sure that they had enough knowledge to present on both the theory application and implementation. So I think it was successful. They learned a lot.
Thank you. Greg, you have a question?
Yeah, I had a question. You started out by saying it was really a pretty small signal in order to people. So when you got all done with this and converted to voltage, how noisy was that? Did you get I mean, was it 10 volts plus or minus 5 volts or 10 volts? How much did it jump around? How much noise did you get out of it?
It would jump around initially, but it would settle down
Can
once.
you use the microphone?
Oh, sorry. So we used a fan to put air through our tubes to get a more steady input, and that really helped get us down to less jumping around. But it would usually stay around like 5-10 millivolts of just kind of noise, as you said.
So like a few millivolts out of how many volts was the signal?
You wanna hear this?
That's why in my data, what I did is kind of like a min and a max over a period of time. Because it would fluctuate around like an order of 10 millivolts. And I think that doing the method that I did would make it the most accurate, taking like maybe 5 or 10 measurements, the min and max, and an average between them is the most accurate.
Any other questions? Dr. Bellan, you've seen this, what, 3 summers now?
Yes.
They have
Yeah, I have
participated.
a question about the waterfall measurement. You had a horizontal axis, but it wasn't labeled. What were the,
Oh,
was
no,
that distance?
that was the distance. It
Yeah,
was
yeah.
distance, I think, from the waterfall.
I see.
You can go back to that. Gilly.
We had the advantage of a lot of water in the waterfall this year. Last year it was a trickle and this year it was a full on
Yeah, there it is. Yeah.
Niagara.
Okay, so that's in feet or meters or?
This is
That's in meters, I believe.
Yeah, meters from the waterfall. So 0 is the waterfall. And then as it goes farther right, it's farther away from the waterfall.
Okay, so you could see a pretty convincing change. You're moving away from the waterfall.
Yeah,
For the air ion count over time, what was the total length of time of that experiment?
for which experiment?
I think this the one in the sun. That was 65 minutes.
65 minutes, so.
I should mention, I was measuring in 5-minute intervals. So to every 5 minutes, I take a measurement, and that's why the points are the data. So, and I had this is all the data I have. It's 5 minutes increments in 65 minutes.
I'd say with that, there's a possibility that the sun was just heating up your instruments and causing it to drift, so you have to convince yourself that wasn't happening. I mean, it could be a correct measurement, but it could also be a drift. I don't know.
That's definitely possible. I would have to do further analysis to get a better result.
Yeah, you could check that by doing it opposite, by having it in the sun and then moving it into the shade, maybe, or I'm not sure if that would work, but so it'd have to be some way of convincing yourself that it's not just the gadget heating up.
Fair enough.
Any questions? Thank you all.
thank you.